actually form these. You can think of them as standing waves, just ways in which the electromagnetic fields like to oscillate inside a grape, such that the maximum electromagnetic field is actually in the center of the grape.
When you put it in the microwave, you see that it heats up not from the outside in, as you would expect, as if it were just absorbing the microwaves, but rather from the inside out.
If you add a second grape to the microwave, you see that the same thing happens. The microwaves get trapped in the second grape too, and the amplitude is highest in the very center of the grape, and so the heating occurs most of all there. But if you move these two grapes close together, so they're closer than, say, a wavelength, well, then you can start to get interactions between the electromagnetic fields in the one grape and in the other. And in fact, if you get the grapes touching, then the greatest electromagnetic field actually occurs at that contact point between the two grapes. And so that is where you're going to get the greatest oscillating electromagnetic fields, and that is where those grapes are going to get hottest. It's also interesting that you don't need to cut the grapes.
So it's an interesting effect that, if you just had the one grape, basically, I think what you end up getting is sort of a kind of a structure like this. So, if you have like if you're talking about a standing wave, then basically the largest amplitude is kind of in the middle. This is, again, a little bit like that standing wave experiment, right? And then, so if you just have two waves like this, two grapes, then two grapes which are separated, then actually the hottest part that you would get would be right in the middle. But actually, so what's interesting, and he doesn't really explain it so well, but I think it must be something to do with the fact that, okay, so now if you've got a box which is actually twice as big, right, then still the ends of this are the nodes here, but then now that the lowest frequency that can vibrate here is going to be actually towards the middle. So I don't know if that explains it properly. So yeah, so I'm actually still puzzled on why actually the largest frequency would be towards the middle here. The frequency should be fixed. So okay. I think that there's still some things which I don't quite understand in this, but nevertheless, it's a pretty interesting experiment where you can actually see, this kind of plasma occurring. And obviously, this is a different effect to the metal case because this is a grape is more or less just water, but in the case of a metal, it's due to the fact that the currents are large. In this case, it's more of a resonant effect where actually a lot of the microwaves just sort of get trapped in there, and then they just start to kind of build up. So just like if you push a swing at the correct frequency, the amplitudes will just start to get bigger and bigger and bigger. And so this is apparently another kind of resonant effect. But yeah, I mean, why it actually goes largest in the middle here is actually still a puzzle to me. If anybody knows, then let me know. Okay, but anyway, kind of a fascinating effect. I think this one we already talked. Oh, sorry, am I sharing the right screen? Yeah. This one we already talked about at some point. So yeah, so in terms of, or no, we talked about something similar with carbon dioxide, not particularly oil, but this was another demo that I was going to do where if you microwave oil and water, then what you should find is that actually that the oil does not heat up as much as the water. This is sort of not what you think intuitively. I think I've heard of a lot of people say that you shouldn't microwave stuff with a lot of oil in it because it'll start to burn in the microwave. In fact, it's not really the case. It's you know, the opposite of what a lot of people think. You know, if you just put pure oil versus pure water, then the water will definitely heat up much more. And you know, again, it's because the microwaves are tuned to the frequency, well, you know, heating efficiency of heating water rather than oil. The reason why, you know, often when you put oil inside a microwave and then it will get extremely hot is basically because if you have a mixture of water and oil, then the water can actually start to heat up the oil, and because the oil does not have a, you know, kind of the boiling point of oil is much higher than for water, so actually the oil can start to heat up due to kinetic energy being given from the water to the oil. But it's actually not because the oil itself is heated, it's actually just because the water is giving the energy to the oil. Okay. All right. Yeah. So, you know, this is actually a little bit complicated, but I thought we should talk about a little bit. But, you know, how does the microwave actually produce the microwaves, you know, in the first place? And there is this device that's called the magnetron. This is basically a, you know, the core of the device that produces the microwave frequencies. And it's actually a pretty, you know, surprisingly, you know, efficient and just, you know, ingenious kind of device, originally developed in World War II to make efficient radar. So originally this was trying to target, you know, generate radio frequencies, not microwave frequencies, but you can use the same principle. So okay, so this is the kind of thing that looks like. It's actually, you know, a fairly kind of dangerous kind of device to dismantle, actually. So you know, if you ever want to, you know, look inside how a microwave works, actually there's many kind of hazardous things inside a microwave. So firstly, you know, there are very high voltages, of course, because in order to produce the microwaves, you need some high voltage electricity. But also there are, you know, some parts of this thing are made of some, you know, poisonous materials. Like I think this pink thing here is actually made of some poisonous material. So it's not recommended to actually take one of these things apart yourself. It's there's kind of a lot of hazards with that. But the basic idea of a magnetron is, again, it's just like a kind of an antenna, but on the transmitting end. Okay? So again, when you want to transmit some electromagnetic radiation, the basic idea is, again, you've got the antenna, you've got something that's going to oscillate the electrons inside the antenna. And again, you have this kind of resonator, the LC circuit, that will oscillate the currents within the wire. Okay, so this is still the basic idea of this. So, you know, we need to make something which is going to be at microwave frequency. So, you know, in a microwave oven, it's like 12.2 centimeters wavelength. And then so, you know, this is the kind of thing that we want to create. Now, the actual device doesn't look anything like this, which is interesting. So, you know, you would think, all right, fine. So we need an LC circuit, we need an antenna, we need something to, you know, drive the current, right? But in the end, the thing to make it looks very, very different to this. So this resonator, the tank circuit, LC circuit, is a combination of the inductor and a capacitor. But somehow people worked out that, well, you could get a real capacitor and an inductor, but even better for the kind of frequencies for microwaves is actually we just need to get a piece of metal that's in this U shape, and this U part of it can act like the inductor, and then basically the U shape, when you have plus and minus charges, this part of it is separated. And so actually this horseshoe shaped thing can be considered to be a type of LC circuit. And well, it's you have to really look at the parameters and materials to show that this is an oscillator in the microwave regime. But well, turns out that it is. So basically, this U-shaped thing is you think of as being this tank circuit. And so this metal thing here that we've got has these kind of holes in it, and then the holes are separated by some gap here. So basically, what we're gonna think of, the way that we're gonna think of this is that basically one of these parts here, this kind of circle and with the gap in it, is like one of these horseshoe shaped things. Okay. And so in this case, this has, I can't remember how many, I think it's like 8 or something, 8 of these kind of horseshoe shaped things. And so you have basically 8 of these LC resonators just by making this piece of metal like this. So this is basically one of our tank circuit elements. And then what we want to do is, of course, to make, you need to connect an antenna to this whole thing. And we also need to drive all these tank circuits at the right kind of frequency. Okay? So what we want to do eventually is we want to have all these horseshoe-shaped things here. And we want to drive them all at this kind of resonant frequency. Okay, and so one way that could be done is by basically having like a piece of metal here in the middle, and by making, say, this side plus, this point minus, this part plus minus like this. That way we can basically have this kind of resonant driving frequency, because, and then this thing here needs to then rotate, because half a cycle later this will be plus, this will be plus and this will be minus, and then basically at each point in time this will be alternating plus and minus, and the next moment in time it'd be minus plus, and so forth. So by kind of like charging up each of these plus sides, with basically a spacing of 1 here, and then rotating this kind of metal thing here, you would eventually produce this kind of drive the current at this kind of frequency. And then finally, so then we want to connect all these LC circuits to some kind of antenna, which eventually broadcasts the microwave. Now, this metal thing, I described it as some metal thing. It's actually not a metal thing. Now, there's an even better way of doing it rather than making this piece of metal, which obviously has some moving parts. And there's an even more surprising way that people actually do this. Oh, okay, forgot that this was an animation. So yeah, so this is basically the kind of thing that we actually want to achieve. But what we're going to do is now replace this piece of metal by some electrons, which are trapped in the middle of this this device. So firstly, so you got this piece of metal, you create a vacuum so that the particles inside it can just move around easily. And then you put these magnets on either side. This is where the name of magnetron comes in. And then you attach a cathode to it, which will basically emit some electrons off the metal. And that's just right in the middle here. This is the cathode. And because of the magnetic field, the electrons will want to kind of spiral. I think we sort of discussed this at some point. You've got a magnetic field and an electron, then it will tend to spiral, circulate. And this orbiting bunch of electrons is actually what we're going to use instead of this, physical piece of metal. So if you've got this magnetic field, electrons tend to circulate, and then this actually naturally forms this kind of this type of shape here that I was talking about. So you don't actually need a piece of metal; it will actually do it kind of naturally. So to be honest, this just totally blows my mind, because how could you ever really think of this thing? It's so far removed from the original kind of basic idea, right? So the basic idea was, so we have an antenna, LC circuit, and then oscillating synchronous. But then you go, okay, well, we're going to replace the oscillating circuit with this horseshoe thing, and then we're going to put a bunch of these horseshoes in here, and then we're going to have an oscillating current, but we're going to create that using like electrons in a vacuum. And it's just kind of mind-blowing how how anybody could possibly invent this thing, but well, they obviously did. So let me just show you.
Noticed.
So you can see how basically this whole structure eventually creates this, naturally just creates this, sort of star-shaped configuration of these electrons. And remember, this is all in vacuum, and then there's a magnetic field on the top. And so this is eventually basically what creates the kind of alternating field, and eventually the microwave. So I mean, okay, maybe this might have sounded pretty confusing for a lot of you, but I think what I want you guys to just sort of appreciate here is that in order to create this, the microwave radiation, at the core of it, there's this magnetron, which really is a super non-trivial kind of device. Like it's as I said, I find it really quite amazed that somebody would be able to kind of design this, because it's just so far removed from basically the original kind of concept. So it really is a remarkable kind of thing. Okay, right. I think that basically is the last topic. I mean, actually, I had many more slides. I think I went through the stuff a little bit too slow. I was going to talk about stuff like Tesla coils and all these kinds of things, and I even had a completely other slide set. There's another sort of diversion that I was going to talk about, which is an interesting video that's been going around recently about how power actually is transmitted in wires. It's another Veritasium video, but this is kind of quite an interesting kind of topic in itself. Just talking about the relationship between basically how power is actually transferred, and also whether there's these kind of thought experiments that you can do, which were showing how actually you might actually get a current that flows in a wire, even though it's actually not directly connected. There's some interesting discussions on the internet. So unfortunately, we can't really talk about those things because we don't have time. So I think we'll leave it there for the content. Now, there's a couple of things that I want to discuss right at the end before we kind of wrap up. So one thing which I want to ask you guys is, so the final exam we will you know, have a take-home exam, and I will send you the questions for the final exam. You'll have 24 hours to do it. Now, I was thinking of doing this in 1 week's time on Wednesday the 18th. Well, we could do it at something like, you know, 10 a.m. Start, you know, I'll send the exam at 10 a.m. You have 24 hours to do it. Is there a preference that anybody has for the day and the time? Because I'm fairly flexible with this. I don't really mind actually which day we actually do it.